Sorry for the interruption, we shall continue. Here is a line that bisects the dihedral angle, and we can consider this something like a 90-degree funnel with our C2 axis as the axis of the funnel. This hydrogen 1, 2, 3, 4. Hydrogen 1 will go to position hydrogen 4 and 4 will come here. Likewise 3 and 2. The rear hydrogen 3 will come to the front hydrogen 2 and the front hydrogen 2 will come to the rear hydrogen, this position. This is one C2 axis, here is another C2 axis. So these C2 axes are bisected by our vertical planes. So these two planes, these vertical planes, this plane and this plane, which are bisecting a pair of C2 axes, are called dihedral planes. Next, I am planning to complete discussion of center of symmetry. Center of symmetry, denoted by I, is a central point in the molecule such that inversion of all the atoms across this central point will bring the appearance of the molecule back to an indistinguishable look. Think of the planar HC double bond C H Cl Cl 1,2 dichloroethene. It is a planar molecule. This is the plane of the molecule. Chlorine 1, chlorine 2, hydrogen 1 and hydrogen 2. Imagine a central point at the middle of carbon-carbon double bond. Let the carbons also be numbered C1 and C2. How is the inversion operation done? You draw a line from every atom to that point, extend it an equal distance in the opposite direction. For example, from Cl1, I am drawing a line to this point, extending it an equal distance in the opposite direction and placing or putting this Cl1 at the new terminus. In a similar way, this C2 is also shifted to this position. The line is passing through the point. From hydrogen 1, you can draw a line, extend it an equal distance, H1 is placed here. Similar operation on H2 will bring it to this position. Carbon 1 will go here, carbon 2 will come here. So after this operation, if I denote it by the symbol I, the molecular look will be exactly the same, but with the numbers shifted in this manner, H1, H2 and Cl1 and Cl2. If one more I is done, it will come back to its indistinguishable identical appearance. So I squared gives the same result as doing nothing on the molecule. But if it is IQ, it is as if only just one inversion operation is done across the center, as we did for plane of symmetry. Here I can write I raised to n is equal to I if n is odd and is equal to identity if n is even. The center of symmetry generates only one distinct operation, which is I itself. There can be molecules with center of symmetry alone. Think of staggered 1, 2 dichloro, 1, 2 dibromo, ethane, staggered. I'll write the Sawhorse projection. Hydrogen, chlorine, bromine, chlorine, hydrogen is here, bromine is here, chlorine is here. Think of the central point of carbon-carbon single bond. It has no plane of symmetry, no axis of symmetry, because all the atoms on the carbon are different. But in this conformation, it has an element of symmetry at the central point, which is the center of symmetry. You can draw a line from hydrogen to this point, extend it an equal distance, and put the hydrogen here. So these two hydrogens are mutually exchanged. These two bromines are mutually exchanged. These two chlorines are mutually exchanged. When the inversion operation is done, the central point is as if it is a central pinhole which takes the photograph of one part of the molecule, and the photograph happens to be exactly like the other half. Just like a pinhole camera doing the photographic work. Such a element of symmetry is called center of symmetry, and the associated operation, drawing a line to the point and extending an equal distance and putting the atom there, that operation is called inversion. In this context, it is interesting to see that there are molecules with a central atom, molecules which look very, very symmetric, but it may not possess a center of symmetry. The best example is boron trichloride. It is a triangular planar molecule. If you number the hydrogens, chlorines as Cl1, Cl2 and Cl3. How is the inversion operation carried out? It has a central atom. Boron is of course at the center of gravity of the molecule. But if you do the operation, I'll do the operation on without shifting it to another place. From Cl1 I draw a line to boron, extend it an equal distance and put the chlorine there. From Cl2, extend an equal distance, you put the chlorine 2 here. From Cl3 draw a line to boron, extend an equal distance, you put Cl3 here. And if the 3 chlorines are joined, I am getting a triangle which is not at all merging with the initial triangular look. As somebody has tilted it, there is no overlapping at all. So this is a central point of course, but it is not a center of symmetry. Another interesting case is methane. Methane has 4 hydrogens. These hydrogens are on the plane of the bow, and we have a hydrogen projected to the front and a hydrogen at the rear. H1, H2, H3, H4. Carbon is a central point. But let us carry out inversion operation from hydrogen 1, draw a line, extend an equal distance, put hydrogen 1 here. This is at the rear, draw a line, it will come to the front, and you will put H3 here. This is at the front, it will go to the back, and you will get H2 here, and this H4 will come here. Initially it was H1, H2, H3, H4. This was the tetrahedron. Now the tetrahedron look is something like this. So 2 tetrahedra are not at all overlapping. They are shifted from each other. So this central carbon is never a center of symmetry. With this description, I am planning to wind up the class for today. Thank you for your patient listening. Questions and doubts regarding this you can put in the comment section. Please do it. Feel free to interact with me. Thank you very much. Thank you.